Yeah, hi. I'm going to present a method that we use to remove the traffic-related portion of CO2 from our tower measurements. As a little introduction, this is our CO2 observation tower network in Oregon that we use for our inverse modeling in the Oregon domain. Those towers are all equipped with instruments that measure CO2 and water vapor in high precision. Some of them are also equipped, also do measure carbon monoxide. We are going to focus here on the three towers in the west, marked in blue here. The Walton Tower and the Mary's Peak Tower are both in the Coast Range Mountains dominated by fir forest. The Mary's Peak Tower, however, is our high elevation tower. It's on 1,300 meters of elevation. That means during the right meteorological conditions, we measure background here because it is above the boundary layer actually, so decoupled from any exchange with the biosphere. And then there's a tall tower in silver, and that is our tallest tower in our network with the highest inlet at 270 meters. All those systems are equipped with Picarro ring down, cavity ring down spectrometers. We run separate inlet lines from each height into a manifold that is controlled by a logger-based valve sequencer program, so we get continuously hourly CO2 and CO concentration values from all heights. Every 50 hours we run calibration gases, and that whole setup gives us an uncertainty, an average uncertainty for CO2 of 0.184 ppm and 7.5 ppb for CO respectively. Those uncertainties include the uncertainty of the measurement, so the difference between the known concentrations of the cal gases and what the Picarro measures during those calibration intervals, the uncertainties of the calibration gases themselves, and the uncertainty that we introduce by correcting those values for water vapor to get our dry concentration values. Most of those towers in our network represent a large, relatively homogeneous ecoregion in Oregon. For instance, the Burns Tower in the very east that represents a high desert area as part of the northern basin and range that is highly dominated by shrubland and grassland. So are the both towers, Mary's Peak and Walton, in the Coast Range that is dominated by fir forest, very dense and vast fir forest areas. Our tower here in Silverton is different. That is located in a very complex area in terms of the land use and land cover in that area. If you zoom in here, that tower is located in the Willamette Valley. The Willamette Valley contains all the urban centers in Oregon. In fact, 70% of Oregon's population reside in the Willamette Valley area between the Coast Range Mountains in the west and the Cascade Mountains in the east. With the in addition to that, we have a dense road network of more than 44,000 miles of road only in the Willamette Valley. And with those come the associated emissions of traffic emissions of carbon dioxide as well as carbon monoxide. This here is an accumulated footprint for the year 2012 at that Silverton Tower for the 120 meter inlet height. That clearly shows that a lot of the footprint is affected by this Willamette area outlined here in blue. So, meaning the values that we measure, CO2 and CO values that we measure at the tower at the different heights, are definitely affected by the emissions in that area. So, a few numbers: transportation accounts for 34% of Oregon's total anthropogenic CO2 emissions, making it the biggest chunk of anthropogenic CO2 emissions in Oregon. In addition to that, 86% of carbon monoxide emissions are emissions from traffic. We can see that in our tower here, the power spectra of carbon dioxide and carbon monoxide, the upper panels A and B show the time series from the Walton Tower, so in the fir forest, and the panel C and D from the Silverton Tower or urban tower. Panel B and D show the power spectra of carbon dioxide, and we clearly see the diurnal cycle of release and uptake by the biosphere here, as expected. Looking at panels A and C for for carbon monoxide, we also have a 24-hour peak in that spectrum at the Silverton Tower, which cannot be found in the spectrum of the Walton Tower, the rural tower. So clearly indicating that the diurnal run of traffic clearly shows in our data. So now, as we heard before, CO2 mixing ratios can be used as tracer for anthropogenic CO2 emissions. However, the portion of traffic-related CO2 at the tower can only be removed if and only if the CO2 emission ratios of those sources, in our case the linear sources, the roads, are known. So we went and measured them in a 3-day campaign covering a little bit more than 1,000 miles of road, different roads. We drove in Oregon covering back roads, highways, city surface streets, and you already can see the high elevation of CO2. That is the absolute measurement value in the urban areas, particularly. That is clearly shown also here in the urban area in the north. That is Portland, and that was taken during rush hour time in the morning. The third day, we tried to cover more the back roads and highways in the more rural areas. I want to show this on day 3. As you can see in the eastern part, there are slightly elevated CO2 emissions or CO2 concentration values. That, however, is not due to any traffic. That is simply because we drove after dusk in that area. That is already the insetting respiration by the dense forest here that increases the CO2 signal. So that's why we had to remove a baseline from our CO2 and CO values that we measured during that drive around, indicated here as a red line. That leaves us with excess values, so the values above the baseline, meaning that those values really represent our sources, namely the roads or in particular the vehicles, and are not affected by any concentrations that are induced by the surrounding biosphere. In a second step, we removed all values, CO2 values of those on-road measurements that were higher than 100 ppm above the baseline. We thought that those are probably more related to very nearby single sources, like very close vehicles, rather than representing the road itself or the vehicle fleet. In addition to that, in the scatter plot, you can see that it scatters a lot more and well, basically ruining our nice regression line. And as indicated by the green triangles, the frequency of those very high excess values decreases exponentially with those very high values. So when we remove that, we get a nice linear regression coefficient of 0.97, so giving us a clear emission ratio. Since we wanted to know a little bit more about what is happening on the road, what is contributing to those CO2 emissions, we got the data from the Oregon Department of Transportation from a traffic count. Basically, we had the information about the type of road, and from the traffic count from ODT, we had the information of what types of vehicles were driving those roads from 2011. So we classified our measurements into 3 final road types with the most distinguishing vehicle compositions, as it is known that the CO2 emission ratio depends on the type of engine and vehicle. So that is what we got for our drive around. The 3 classes are the interstate and freeways, the city surface streets, and the rural streets. Under that you can see the road type classification, the original 3 classes. So those are actually the vehicle classification. It's clearly shown that all of our final road types are dominated by simple sedans and small passenger cars. However, there are differences in the type of vehicles, especially large vehicles, large trucks that are mostly equipped with diesel engines rather than gas engines, if you look in classes 5 and 9, for instance. So those are our final emission ratios now for these road-specific final emission ratios. it's clearly shown that the city surface street have the highest emission ratios. That can probably be explained by the fact that we have a lot of cold starts and short drives in the city that is associated with higher carbon monoxide emissions and incomplete combustion processes in the engine. That looks actually a little better on the big interstates and freeways. Mostly could be explained by we don't have those cold starts. In addition to that, we have a larger portion of diesel vehicles with generally lower CO emissions. Our weighted average of 7.43 ppm fits very well in the trend if you compare that to measurements over the last 15 years in the US. And it clearly shows that over time, with the modernization of the vehicle fleet, the CO2 emission ratios decrease, and our value shown here as a red diamond here on the right is pretty much fits into that trend. So now we wanted to use our CO2 emission ratios to remove the to remove the traffic-related CO2 from our tower measurements. So for that purpose, in order to compare it to background measurements at the Mary's Peak Tower, when it's decoupled from the exchange, we have to first remove the CO2 from the biosphere, so the uptake and release. That we could do with our CLM 4.5 model that delivers us a priors for our inverse modeling system. So we basically just multiply our WRF footprints with the NEE and get our our biosphere-related delta CO2 that we can remove. In the second step now, we used our emission ratios that we calculated and removed that using the CO measured at the tower, and the CO2 baseline, however, was taken from the tower in Walton, just because that is located in an area where no emissions from traffic are abundant. There's, it's in the dense forest. There's no urban sources or large traffic sources anywhere nearby. So when we remove that, we get our CO2 background by just removing the biospheric CO2 and the delta CO2 from traffic from the measured CO2. In order to get the real background values from our Mary's Peak Tower, we made sure that we meet the right conditions. So those data that we used had to fulfill those three criteria. First, the footprint strengths had to be very low, basically indicating that there is no exchange between the biosphere and the atmosphere at that time. Secondly, we only took wind directions from the west-southwest. And thirdly, the correlation coefficient between the Walton Tower and the Mary's Peak Tower had to drop significantly. Usually both towers the time series of those towers are highly correlated. They're in the same ecosystem. Usually there are correlation coefficients of 0.9 and more. During those conditions, when the background is measured, it drops. So now we could compare our measured CO2 background with a corrected CO2 background. The first column shows a direct comparison. Second column shows after we remove the CO2 from the biosphere. And the third column shows the final comparison, basically, showing that the correlations increase with every correction step, which gives us confidence that that all makes sense. Last but not least, a little conclusion. We measured the CO2 emission ratios directly at the sources, and the values we got fit into the original trend, and the additional uncertainty is 0.86 for the corrected CO2 measurements, which is an important value if you think about the inverse modeling that those values is used for. Thanks to my collaborators for their contributions and to you for your attention. Thank you.